uh, the scientific method says it's impossible to prove that a hypothesis is true. What it does is it relies on refuting the null hypothesis. And the null hypothesis is the exact opposite of the hypothesis, and it's constructed in such a way that it's mutually exclusive. So you can't have a case where both the null hypothesis and the hypothesis are both true or both false. If one's true, the other has to be false, and vice versa. And so the hypothesis I was testing was that the Earth is a globe. The null hypothesis is the Earth is not a globe. And my goal of the experiment was refute that. Refute that the Earth is not a globe, so we know yes, the Earth is a globe. But unfortunately, I can't refute it. Everything is showing is way closer to flat than it is to the globe. So that was the purpose of the experiment.
But couldn't
Right.
it be phrased just the other way and swap the null hypothesis with the non-null hypothesis or whatever, and say, well, it doesn't match flat, therefore it must be a globe?
So you can do that, and professors will teach you that if you find the exact opposite of what you expect for your hypothesis, if you can't refute your null hypothesis, just switch them. But I think if you switch them and your hypothesis is the Earth is flat, um, you're coming up with much better evidence that the Earth is flat than you are that the Earth is globe. So I'd have to say the null hypothesis achieved its goal, especially with the very first experimental result, where Pike's Peak was flat to within the accuracy of the measurement. Now, several of the other peaks I've tried, they're not quite that close, but they're still extremely close to flat and not close to globe. Um, some of them are dead on, some are off by like 50 meters. And um, and I haven't done any testing to see how accurate is this method I'm using. Like if you're sometimes in the videos, it's hard to because of the extremely long time exposure and the star trails that Jesse noted. Sometimes it's really hard to pinpoint when was that star actually occluded versus the time lapse of the star trail being occluded. So that's going to introduce an error, and that introduces an error that would make the measurement appear lower than it is. And despite all of the efforts to eliminate refraction, we all know there's a little bit of real refraction present. It's just negligible for the accuracy we're trying to achieve to differentiate between flat Earth and globe Earth. So and that could make things appear a little high. Now, on both of the Green Mountain photos, you can clearly see clouds present at the beginning of the video before it got too dark to see them. And clouds would create more refraction, and that could be the whole explanation for why the measurement is high. But in any case, it's extremely obvious. It's nowhere near what it needed to be for a globe Earth. It tends to favor the flat Earth hypothesis. And there's probably a moral in this, which is we probably shouldn't try to analyze videos that are too dark to make anything out. And we should stick to the ones like some of the earlier videos where it's really easy to see the mountain, it's easy to see the star, it's easy to see if there's clouds.
Real quick, Dr. Mike. So, Jesse, do you agree with Dr. Mike's assessment so far and what he stated about the other measurements being more close to flat than globe?
No. Blodgett Peak is between flat and globe, but closer to globe.
Okay, that's one peak. What about the rest?
Was that the peak that you and Piezo went over?
Yes, that is the peak to end.
Okay, yeah. So that was the one where the angle was probably wrong or whatever, because if you switch it, the two columns flop. We talked about that earlier, but so we'll have to touch back on that.
Yeah, well,
But
we did our math from the ground up using just the raw data, not relying on anything else in the spreadsheet, just the timing and the star. And I did want to respond to the suggestion that clouds were making all those stars appear to set 2,000 feet too high. Because I traced out the mountain skyline when it was visible at dusk and superimposed that on the video, we can see that that is the terminator line. That is where all the stars, throughout the whole video, they all occlude at that line. So there were no clouds. It was the same mountain profile that was occluding the stars the whole time. And you mentioned, Mike, also that you expected the peak on the right to be lower. If you rotate the video 3.81 degrees, so that the star patterns match stellarium, then it is lower on the right. And now that we have the formula to predict the celestial theodolite angle based on observer height, mountain height, and distance, it seems very reasonable that we will be able to get as many perfect globe results as we want by just adjusting the distance, by changing the distance of the observer. Because I tested the simulator on all of, let's see here, I did it on, let's see, Pikes Peak, Blodgett Peak, Cheyenne, Mount Rosa, Blue Mountain, Green Mountain, and Greenhorn Mountain, and it matched all of them. So I think it does accurately predict what will be found, and it predicts lots of situations where we will get perfect globe results. So how would that affect the null hypothesis if we are getting more globe results?
I haven't had a chance to look at your simulator, and all I know is what other people have told me. I got a couple of equations I briefly looked at, and the equations I looked at look like they're adding refraction in, and so I'm skeptical that the simulator can do what you claim. And there again, you're missing the point that the object of the experiment is not to find a distance where it agrees with flat Earth or globe Earth. It's from whatever distance it's actually observed from. Does it refute the null hypothesis? That's the scientific method. That you have to always realize a hypothesis can't be proved. Therefore, it's necessary to refute the null hypothesis, and being able to predict what the null hypothesis will show does not refute it. In fact, if anything, that validates that it couldn't be refuted because you can predict what it is. So, the experiment does not take refraction into account. It's pure, how far away are you? Okay, now that you know how far away you are, multiply that by the tangent of the elevation of the star when the peak occludes it, and that gives you the rise above the observer. Now add in the observer altitude, and you've got what we would predict the altitude of the peak is, and then my spreadsheet just looks at the difference in the measured altitude of the peak versus the official altitude of the peak. And in all cases, and somebody's going to have to bring me up to speed on the alleged discrepancy on Blodgett Peak, because this is the first I've heard of that. But on my spreadsheet, even on Blodgett Peak, the measurement was much closer to flat Earth than it was to globe Earth. So I don't think the simulator is a valid thing, because by your own admission, the simulator predicts the angle found for the null hypothesis, which means it's failing to refute the null hypothesis, which means the hypothesis is presumed wrong.
No,
And so the Earth is not a globe.
no, it doesn't predict the flat Earth results. It predicts the actual angles that you got in each of those different situations, including the Blodgett Peak one and the Cheyenne one that were about equidistant between flat and globe.
Okay, so if it predicts those, it's predicting elevations that are more in agreement with flat Earth than with globe. So it's still not refuting the null hypothesis that the Earth is not a globe. It's validating that null hypothesis that the Earth is not a globe because the numbers are what you would expect from a globe Earth.
No, it's predicting observable reality. So it says that if you got 16 miles away from Blodgett Peak at the same observer height that you were, that you would get a perfect globe match, for example. And so my question is, when people start
Blodgett
using
Peak
this,
wasn't.
when people start using this,
Blodgett,
go ahead.
I was just going to say, Blodgett Peak is not 16 miles away.
No, but you could drive closer to it. And
Right, but so now you're speculating. You're speculating. You're not using the actual measurements anymore. So you still have not. You failed to refute the null hypothesis, and that's the problem. The whole goal of hypothesis testing is you have to be able to refute the null hypothesis, and you can come up with a simulator and contrived measurements and say, well, if I was half the distance away, this would work, but we have no evidence that that's true. So we have to go by the actual measurements taken, and do those measurements refute the null hypothesis? And the answer is no, they do not.
Okay, but now that we know how to easily use the method to get globe results, when those globe results come, when people actually go out to the locations needed to get the globe results using this method, how will that affect your hypothesis?
So there again, it sounds like you're trying to contrive a scenario where what you want to believe will agree with the way you're trying to make it happen. And that's not how the scientific method works. The scientific method is you have a hypothesis. In this case, the hypothesis is that the Earth is a globe, and therefore the land should curve away. And when we measure mountain peaks, they should be a certain number of meters lower than a flat Earth would predict they are. And all of the experiments I did are not picking and choosing a location that makes things work. It was taking the peak where it was, taking the observer where it was, not driving to some special location. The first few measurements from my sunroom and the rest was from my front yard, since not all the peaks are visible from my sunroom. And all of those measurements fail to refute the null hypothesis that the Earth is not a globe. The measurements show that the Earth doesn't appear to be a globe just from those measurements taken where they happen to be. So what I hear you arguing is if you fudge the data, if you find the ideal location and the ideal peak, you can come up with something that agrees with your expectation, but that is not the scientific method, cherry picking data. You just have to take the data as it appears.
I had a question on that. Is that how science works? You could falsify something, like you could falsify something, then somebody else could do science and then unfalsify your falsification.
That's not the way a null hypothesis works. A null hypothesis is the one thing that cannot be true for the hypothesis to be correct. And because you can't prove that a hypothesis is correct, what you have to do is refute the opposite of that hypothesis. So the scientific method is refute the null hypothesis, and then you from doing that you can quantify your level of confidence that the hypothesis is correct. In this
I know.
case, in all these measurements, our confidence that the hypothesis is correct is extremely low.
I know, but
oh, go ahead.
I'm just saying, somebody could come along and falsify your falsification? They could unfalsify it?
Well, they would have to come up with basically they'd have to use the null hypothesis as a hypothesis, and then they would have to falsify what was the original hypothesis. So I think you can see the problem that to falsify if the hypothesis is that the Earth is flat, what you have to do to falsify that hypothesis is the null hypothesis has to be the Earth is not flat. And when you set about to falsify that null hypothesis, that's when you discover to your amazement and horror that the evidence seems to show that the Earth is flat.
So
Yeah, but they would have to have data that shows the opposite is the key too. You'd have to actually have.
They don't have
evidence.
any data, right,
Right.
Gio? They
Yeah.
still haven't presented any of their own occlusion timings that counteract our observations or our timings.
But that's sort of what Jeremy is almost getting at, is that, yeah, if something's been falsified, if something has been falsified with data, could you then try to falsify that falsification? But in order to even do that, you'd have to have data that shows something
Your
different.
own observations, right?
Yeah, and repeatable actual measurements and data that would show something to the contrary.
Yeah, but I'm saying
Yeah,
though, like
so-
once you falsify. Sorry, real quick. Once you falsified something, how could, like, unless your methodology was wrong, how could you unfalsify your falsification?
by
How could Jesse come along and undo what you did unless your methodology was flawed or something?
right, by invalidating
So-
the
so-
methodology.
Yep, and so that's a good point. Once you falsified it, and so you can't unfalsify it. But what you can do is you can swap the null hypothesis with the hypothesis. So instead of starting with the hypothesis that the Earth is a globe, you could start with the hypothesis the Earth is flat, and then in that case, the null hypothesis would be that the Earth is not flat, but it does take an entirely different set of data to falsify that null hypothesis. And what this entire experiment inadvertently discovered is that the data is showing that the Earth is flat. So it's going to be a hard hypothesis to falsify.
Well, I have a question. If I can drive to a certain point and then follow the method and get globe results, does that invalidate the method?
And the answer is no. It's cherry picking data. If you're driving to a particular point that falsifies it, I probably a good example is my doctoral dissertation, stochastic analysis of progress tracking metrics. To falsify my hypothesis, what I had to do is simulate 3,000 years worth of software projects using stochastic data that modeled real world collected data and show that null hypothesis was false for 90. I think the standard they held me to was 95%. So I had to show it was false for 95% of those simulations. And nowadays, people are doing things with models and simulations. I personally prefer the old scientific method where you have to go out and do real experiments, not simulations, because it's too easy to make mistakes on simulations. It's a lot harder to fudge real world data.
Right, but here's the thing, though. The Globers have been telling us for years you can't prove things using science, which I could debate everyone on that thinks that. But so you're saying we can't 100% falsify things now either? Because if somebody
Well,
can come
no.
along and unfalsify you, like now what? You
Okay,
can't
so
falsify
like what
things.
he's saying is that for Jesse's thing, he would have to say that like 95% of the data like matches the globe. But what Dr. Mike is saying is that wouldn't be the case. If you're going to a particular location to take the data, then you wouldn't have 95% of the data match it unless you're like cherry picking, which would mean that you'd only go to these places to test it.
Yeah, like let me go
Dr.
to a
Mike
place
didn't
within
go to
2
a
miles.
place to test it. He just went where he had it, you know. He wasn't going to achieve certain results. He was just where he was at, took multiple different measurements. But like, you know, to do it the other way around, you would have to, say like that 95% data matches this, and you're not just like picking, you know, one particular location. I think that's what they were saying.
So
But
The close.
you can't 100% falsify things in science either. Then is that what we're?
So on Ether Roundtable 63, I did a presentation called "It's Debatable," where I went over how to go about falsifying the null hypothesis, and it's all about level of confidence. So you can never prove a hypothesis to a level of confidence, but you can refute a null hypothesis to a level of confidence. Most doctoral dissertations require that level of confidence to be somewhere between 95 and 99%. In the case of that presentation, I falsified the null hypothesis to 6 sigma. So it was 0.999999999% certain that the null hypothesis was refuted. But you're never entirely certain you've refuted it. The scientific method is a search for truth, so there's always uncertainty involved. And when you dig deep enough, you always find anomalies, and new knowledge lies in those anomalies. So one of the things we should be doing is explore all the anomalies. Sorry, I'll be quiet and listen.
Well, I actually had a question for you. What would be the reasoning as to why you can't prove things? I sound like a little kid. Why can't we prove something 100% using
But
the
we're getting
scientific method?
hella
What's the
off.
reasoning?
We're getting hella off topic.
can I ask a question?
All
Yes.
right.
So what if I just happened to be in the right location to get a perfect globe match using the method? Would that be different than if I had intentionally driven to the location that gave me the perfect globe match?
Yeah, if you could show different distances at that same globular location, like Mike did, that would be like, oh, okay, cool, it's ambiguous or whatever.
I mean,
That'll do it.
I mean, if I'm following the method to the T, does it matter why I am where I am? I mean,
Yeah,
the
it
method
matters how
doesn't.
far away.
So yeah, I've heard you say something several times that tips me off to the piece you're missing. For you, apparently, distance matters. With the method I used, distance did not matter. I observed peaks at various distances from a relatively fixed location. For all practical purposes, it was from the same spot. So it was various distances, and each of those distances refuted the null hypothesis. And that was using peaks that were just where they were. I had no control over them. So I didn't happen to luck out on all those peaks. Those peaks were where they were, the distance they were, and I had no control over any of that. That's what you have to do with the scientific method. You have to take the data the way it appears.
Yeah, you weren't a flat earther before these observations. You just wanted to help Taylor out with her theodolite observations and etc. And you came to your own conclusions, and we heard you out, and we're like, holy shit, this is a great concept, the celestial theodolite. taking the timing of when a star gets occluded by a mountain peak. Therefore, you can remove the refraction argument between the observer and the mountain peak and actually get the true geometrical location of the star using stellarium. And it's like, you didn't expect it to match, but it matched. And then to confirm it, you did other peaks and other stars at different times. What has the globe shown?
Yep, and I'd only add that I don't think Taylor needed my help. In fact, I'd say she was more of an inspiration. That she inspired me to get off my butt and use the scientific method to try to determine is the Earth flat or is it a globe? And to my surprise, it was flat.
Impressive. Thank you, Dr. Michael.
So if I have a spot picked out that should give me globe results. It's 24.73 miles from a mountain that's 2,337 feet high. If I go to that spot and follow the method to a T and it matches the globe, does that invalidate the method?
The first sentence out of your mouth invalidated your method, because you're saying, if I go to a spot where I expect to get the results I'm looking for, is my method invalid? Well, yes, it is. If you're going to a spot that you're certain is going to prove your hypothesis, you're doing it all wrong. The whole purpose of stochastic analysis for my own dissertation was everything was random. I had no control over what was happening in the simulation. All I could do is let the simulation run, collect the data, and after the fact, analyze the data where it lay, to see if it was within 95% refutation of the null hypothesis. And luckily it was, and they approved my dissertation, and I got my doctorate.
Well, so what if I just happen to be at that same park just for fun? Maybe I take my sweetie out there or something and it gets dusk and I time an occlusion from that same location, but because I was already there for other reasons and then I get globe results, then does that invalidate the method?
Is that what you did, Jesse? Path
Yep,
of Light?
your location's tainted. You have to take your sweetie to a new location, completely randomized.
Yeah, I mean, I guess in a way,
Yeah,
when Jeremy brought up the like falsifying a falsification, this is in a way, Jesse, this is what you're trying to suggest, is that if you go out and get globe results, does it then? Now you keep saying it invalidates his method. Do you mean it invalidates his data or his conclusion or the actual method? Because if you're following the method and saying the method gave you globe results, then obviously you would have to say the method is valid if you're trying to say it's a globe. But the point he mentioned as well is that if you're going out, seeking a certain result, then that's already a different intention to begin with.
Well, the point I'm making is
It's a rigmarole.
if the distance has such an effect on it, such that it allows the results of the method, when correctly followed, to match flat or globe, then wouldn't that invalidate the method as a way to determine flat or globe, if it could give either just depending on the distance?
I disagree with your contention, because if you look at Mount Rosa, for example, it's a different distance, and it equally shows from my observation location that it's a flat Earth result, not a globe Earth result. And all of those peaks were far enough away that there's a clear distinction. It's easy to tell the difference between a measurement that supports globe Earth and a measurement that supports flat Earth. And that's what you're looking for. So if you just happen to drive out to some location and you just happen to take a measurement, and your measurement says, oh, well, I can refute the null hypothesis the Earth is flat. Now what you want to do is what I did and look at other peaks and see, are they all refuting that the Earth is flat? Or was that one just a fluke? Because that Blodgett peak was the second one I did. And that's when I realized when you get too close to the peak, there's not enough difference to have a high level of confidence that you're seeing the difference. Like you said, it's pretty close to, it could go either way on that particular peak because I'm just too close to the peak. Choose your peak level of confidence that you're seeing the difference. Like you said, it's pretty close to, it could go either way on that particular peak because I'm just too close to the peak. So you want to choose your peaks. You want to choose your distance such that there's a clear distinction between flat or globe.
Well, so that it does sound like you're agreeing that based on the distance and the height and the elevation relationship, you could get flat or globe. So there's something missing.
No, I'm not really saying that.
Well, if
no, so you might want to spin it that way, but that's not at all what I'm saying. What I'm saying is, yes, if you get too close, you can't distinguish between them. That's not that's not refuting the method. That's missing the point of the method, which is to be able to clearly distinguish.
Exactly. So if you get closer, or like how Daza was saying, like, oh, why don't I use a peak that's only a mile away? Well, because the difference between flat and globe is so minute, you can't tell whether which one is true or not. That's why the distance has to be exemplified, right? The longer the distance, the more different between the flat prediction and the globe prediction. Because if you're on a globe, then the mountain peak would be tilting away from you and be lower. Thus, the timing would be different. So you guys still have to show those timing occlusions that match the globe. And the only way you can do that is if you do the same exact way, the method, right? Accentuating the distance between you and the mountain peak. It has to be enough distance to basically show a huge difference in arc seconds.
You mean arc minutes?
I mean arc minutes. Sorry. But yes.
So you'd agree that a broad random sample of points would be better than a sample from one fixed location, right? That we get a better understanding.
Yeah, bring it on.
We're waiting. So the other scenario that's going to overwhelmingly cover all of the points, right, is the setting of a star on the horizon.
Oh, do you hear Daza, Alan?
Yeah.
Yeah.
I was trying to answer his question.
I think it's like 7 or 8 mountains, right?
Yeah, we have different distances already.
Yeah, don't we have like 7 mountains?
Yeah,
all at different distances.
Lodge Peak, Cheyenne, Mount Rosa, Blue Mountain, Greenhorn Mountain. How many is that?
7.
Yeah, but you need to do some from sea level, different atmospheric conditions, because we know that impacts refraction, right?
Dr. Hefron, I was gonna ask you, did you ever confirm the location of the stars if they're saying like this is not the location of it because it's being refracted, so like stellarium's wrong, but have you ever tried to get the angle of the star with your what's it called, your sextant? Just so I confirm that it's actually there if they're saying it's being refracted.
So I haven't. I've only heard that argument with respect to Green Mountain, and with Green Mountain, because it's so far away, it's so dark. It's hard to positively identify any of the stars except for the way Jesse did it. I think Jesse, where he overlaid stellarium in the actual video, that's an excellent way to confirm the identity of the stars. But I have not tried to do that, and the reason I haven't tried to do that, the whole premise of the celestial theodolite is there is nothing more accurate than where the nautical almanac says the star is. So I don't need to confirm it. I just need to know what time the peak occluded it, and I do know where the peak is.
So
distance and angle equals height, yeah.
And I think as to the azimuth of the peak, we can pretty much conclude that if we know the occlusion time, we can get the azimuth of that occlusion point from stellarium, right?
I agree.
and then we can go into Peak Finder or Google
Off
Earth,
the mountain, not from his location.
and then we can go into Peak Finder or Google Earth and then see where that azimuth lies, and if it lands right on Greenhorn Mountain, then yeah, it's probably Greenhorn Mountain. If we know the star, and we know the occlusion time, we can get the azimuth angle. If we've got the azimuth angle, we can tell the mountain it clipped behind.
I think that doesn't work because, once again, you're going to predict a different angle to the mountain than we do. Because the mountain should be at a certain angle, and then you add refraction or whatever. So you're going to have to like try to use refraction to make up the difference between the predicted versus actual. But that's why we transform to the location of the mountain peak to get the angle to the star. We don't tell Stellarium where we are. I don't think Stellarium's going to be able to tell you where the mountain's going to be. Only the star.
So this is my proposed site. It's 24.7 miles. The mountain's 24.7 miles away, and the difference between globe and flat is about a little over 10 arc minutes. So that should be usable, right? That equates to like over 400 feet, right?
Yeah.
That equates to like over 400 feet, right?
Yeah.
Okay, cool.
10 degree arc minute difference between flat and globe. That's kind of hard. That's not really, not too. It should be a bigger difference.
No, that's plenty big.
Yeah,
10
arc
seconds.
10 arc minutes
10
is.
Arc
10
minutes are
arc,
big.
10 arc minutes is going to be like, what is that going to be like, 20 seconds, 30 seconds, something like that?
Something like that, right? It's 4 seconds per arc minute,
Yeah.
right?
So that's significant.
Okay. All right.
Yeah. And I'm going to try to have my cameras synchronized to atomic time from WWV on 10 or 15 megahertz as well.
Respect.
Okay. All right, cool. I look forward to it. At least you're bringing something on the
I'm
globe
trying.
side.
So Jesse,
So,
you're claiming that'll
real
be that'll be a raw measurement then? You're not going to add any calculations in order to get your result? It's just going to be straight observed? Is that what you're claiming? Or is
Well,
there going to be a post processing?
Well, the first step is simply record the exact occlusion time of a star, of a known star at a known location. And then I'll just upload that as a video, and then you guys can apply the Hefron method and see what you get.
Got it.
Fantastic.
And the simulator, which matches all of Dr. Hefron's other CT angles, says that this one is going to match a globe, so it'll be interesting.
Wait, you mean the one where you plugged in celestial refraction?
Yes, sir. Hey, it predicted every single other one of his except the March, the earlier March one for Greenhorn, which had misidentified stars.
And you say it predicted, but it seems more like there's a bunch of arbitrary coefficients in here in these various lines of formula that you plugged in.
Well, most of the math is simply astronomical refraction, which is kind of convoluted.
Yeah, well, where did these arbitrary coefficient numbers come from? It looks almost like you plugged in all of his observations in an Excel spreadsheet and did a form-fit plot curve and took the formula and plugged that into Desmos.
Oh, no, let me get it for you. The astronomical refraction stuff all came from a PDF that Shubil gave me, and I will copy that page to you. Hold on.
Because I think we have, if we go back to one of those first versions of Dr. Mike's Celthio Prez Allen, remember that chart he had with the celestial refraction formula on it?
Yeah, from GG Bennett, that gives 15 arc minutes or whatever for like a uniform, correct?
Yeah, can you pull that up real quick? Because I want to compare that formula to the one on this Desmos thing. Because I could have sworn the coefficients are different.
I tagged you, Aetherboy, with the formula that we used for astronomical refraction.
My dude said Ether Boy.
Ether Boy.
What are you talking about, dog?
It used to be Ether Piezo, right? Piezo? Ether?
Do you mean Crystal Wizard?
I don't know.
Address him by his title.
Yeah, it's this one. Keep going down. Oh, right there.
Yep.
Yeah, that is not what they have. So here, right here, let me pull it up real quick. We've got, yeah, completely 34.133 plus 4.197 times the predicted angle, and yeah, we've got some here. I'll show you. Let me just put it in chat. Follow up with what Jesse just posted.
Yeah, we just transcribed the formula from this this page out of some book. I don't even know where it's from, but Shubil gave it to me because I asked him how to calculate astronomical refraction, and he gave that to me, and so that's what we put in there. Nothing
I
was
see.
fudged or fitted
Smart's
to
formula.
any data.
Smart's formula. And what is h squared in Smart's formula?
I don't know. I just used it, and it matched Stellarium reasonably close, and so we went with it. We tried to use Stellarium's code from their astronomic refraction correction, but it's like got multiple parts in it, like interpolates between them, and eventually we gave up trying to code that into Desmos and just used the formula from the old paper that Shubil gave us.
Oh, hold on real quick. Well, you say you don't know what H2 is in this formula? You used it without knowing what it is?
I figured it out months ago when I was converting it to Perl, and then I kind of forgot what it all meant. And then Pink Floyd helped me, and he just recently used this to put it into he helped me with the Desmos.
Right, so I'm looking here, and it's saying H2 is measured in degrees. This is, okay. This is them applying a correction to the, like, standard angle, right? But this is using a globular baseline, right? So...
No.
the Smart was trying to calculate refraction on a flat Earth?
No, just refraction. The apparent displacement due to the atmosphere.
Right, but that's presuming what model?
It's just a formula that closely
right.
approximates what they. Anyway, it's
But
close. It's close to what's in Stellarium. Take it or leave it. The fact is, we took a boilerplate formula for astronomical.
You can't just walk away from the question like that, dude. It has to have there's a model underlying the math that's being used here, right? Because the prediction would be totally different. I just find it very odd that you would apply a celestial refraction formula to a mountain and it would make up the difference.
We're applying it to the star.
Well, you're applying it to the star, but it's crossing it at the point of the mountain peak. Isn't that the same thing as applying it to the mountain?
Nope.
If they coincide with one another at a point in space?
Yes, it's
well,
the same.
Look, where the formula came from, we didn't curve fit match anything. It's just a refraction.
Real quick, Jesse, I have a question for you. Sorry.
Huh?
Are you moving the star up to the observer at the location rather than at the peak?
Well, I'm not really doing anything. I simply came up with a formula that models the method that Dr. Hefron describes, which allows it to predict, based on observer height, and mountain distance, what angle the Hefron angle will be. It's just like going in and doing it in Stellarium, but you don't have to actually go out and do it because it predicts it. It's a simulator.
So can you tell me which color mountain is for the glob and which one's for the FE?
Yeah, the higher one is the flat Earth mountain, and the lower one is the globe mountain.
So the purple is the
globe.
Okay. Wait, what?
Well, okay, let me look. I don't have that open right now.
I'll pull it up.
I don't know. The higher one's the flat Earth, but let me look. I got so many.
I think the purple's higher.
Yeah, the purple one is the flat Earth one. The green one's the globe Earth one.
Okay. And then I'm also looking in here, and you have this apparent angle equals FE prediction angle minus D times 22.2 over 36. Where'd you get that 22.2 from?
That's just the arc seconds per mile that something drops in the distance on a 7/6R globe. It just calculates the apparent angle to the mountain. The fact
On a
is,
7/6R globe.
yeah. So in other words, at any point, if you are looking at an object that's at a distance that should be, say, the same height as you, the angle to that will drop at 22.2 arc seconds per mile. For whatever
Wait a
reason,
second.
that's just the way it is.
You said 7/6R. You're talking about standard refraction. But the apparent angle right here is for the star.
No, that's for the mountain.
X apparent angle. You're saying that's for the mountain.
Yeah, that's the apparent angle to the mountain, which happens to be also the apparent angle to the star at the time of occlusion.
Okay. Astrorefraction equals astrorefraction raw, which is the formula you plugged in from there, times adjustment for atmospheric refraction. Why are there
Right.
two?
Well, look in the page from the PDF that I pasted. You see there's that second part, probably the yellow part. I don't remember. It's been months since I actually converted that to Perl scripting, and then it was P. Floyd who just recently did it into Desmos. From this same
Okay.
paper.
And you have Hefron equals apparent angle minus astrorefraction plus D over 69.0468. Where'd that number come from?
Well, D is just distance in miles, and then that's 69 degrees per mile. Or 1 degree per 69 miles.
1 degree per.
Yeah, per 60 nautical miles.
Okay. And you're saying that if I adjust these sliders, what will happen?
You can change the Hefron angle by changing the sliders, and you can also change the mountain height and the observer height by changing the sliders, and you can find the combination you want that creates, or for a given observer and mountain height, you can find the distance required to make it match either flat or globe.
This K mountain width is just arbitrary, just to make the mountain wider for preference, right?
Yeah, this is for fun. Because, like, if you're...
And this T is what? What is this T?
Temperature in centigrade.
Okay.
Because that affects that's one of the inputs to the astronomical refraction. So that affects the red line a little bit. Not much.
How would the mountain refracted, like, block if they're both refracted, like, you know, I could understand maybe the star for this case, but the mountain too?
I don't see any combination of observations where this red line crosses the green mountain.
Can you stream what you're showing, Piezo? Can you stream what
hold on.
Showing?
Hold on. Yeah, 1 second.
So if you put in the heights, put in everything for Blodgett Peak, and set the distance to 16 miles, and then it'll cross the globe Earth mountain.
Blodgett, hold on. Set the distance to 16 miles.
And this is also in feet and miles, not meters. Sorry, but I can get those for you.
Blodgett Peak.
So you're moving it closer to match the globe.
Right, exactly.
Why?
To make it indistinguishable to try and corrupt the method. So this is the inverse of what John did. So whereas John went to the extreme at 1 mile, Jesse's going slightly longer. Right?
Yeah,
but
so if you notice, right? So here's the thing. If this angle for celestial refraction is correct, or this formula rather, if this is correct, right? Like this is accurately modeling the behavior. This should be precise, plus or minus like 1%, right? I mean, at this point in modern science, then this red line should be comporting with that green thing all the time, not the purple thing. This green mountain is the glob, and this purple one's the FE, right?
Well, if the method was unambiguous, if it worked regardless of distance, then yes, but it doesn't. You can.
Well, you're plugging in refraction in order to say it doesn't fit with the FE prediction, right? I mean, like.
Yeah, we're doing ours with a raw geometric position of it, and just the planar trigonometry.
Well,
so what
so
you're
far,
trying
no
to do
tricks.
doesn't seem.
There's no
quite
tricks
the
being
same.
played with the flat Earth version.
regardless of whether you understand or agree with the validity of the math, the system works. It accurately matches every single one of Dr. Hefron's tests so far, except the two first ones for Greenhorn Mountain, which had misidentified stars.
Hold on, wait. This formula right here, you just told me this is the apparent angle to the star, right?
Well, to the mountain, and it's the same as the star because it's at the moment of occlusion.
Well, hold on. It can't be the same as the star because this line's not crossing this mountain right here. So is this apparent angle for the mountain or the star?
Neither. That's the Hefron angle. That's the result. That's the altitude angle, the unrefracted altitude angle that stellarium gives you in the final step of the Hefron method.
No, this is X. This is the Hefron angle right here, X Hefron. This right here is apparent angle. Hold on, I'll tell you what. If I just change a number, I can see what changes. Yeah, it's definitely to the star. See how that line to the star changed? Okay, so you have the apparent angle to the star being the FE predicted angle minus a 7/6R Earth correction. So you're applying that position to the star in this model that has both mountains. You would need to have two different lines. You need to have this apparent angle be the one for the glob prediction, and then have a separate line that doesn't incorporate refraction for the other one.
Well, that's the beauty of Desmos. It's free. You can take and make a copy of this and modify it however you like. And at the end of the day, though, my version matches all of Dr. Hefron's data points, valid data points. So, I mean, you can modify it if you want, but you can't make it any better. All you could do is make it so it didn't match all of his data points. But so far, it matches all of his data points, and it was not fit to his data. It was made from other independent sources just based on the geometry of it.
But wouldn't you be assuming the curve? Like if you're using the 7/6R, which assumes the curve of the Earth, wouldn't that be already assuming a shape? How would you be then testing the shape?
So the reason it does that is because it needs to know the apparent angle to the mountain, and that just happens to be, even if Earth is flat, for whatever reason, that is the formula that gives you the apparent angle to a mountain. And so I'm just using that because it gives the apparent angle, the accurate apparent angle to the mountain.
But is the mountain apparent angle assuming curvature or not?
Well,
it should be in the paper that he linked, right? Like that's the question I asked him. He's like, it doesn't matter, it just does work. And I was like, no, bro, like it matters because there's an underlying assumption. Because if you were to say that works on a flat baseline, it would be there would be a different distance or a different height delta across distance, any distance.
Yeah, it fits the refraction curve or whatever.
But also one of my biggest problems, I haven't
degrees.
had a chance to like analyze this or anything. But
yeah,
just
take your time,
at first glance,
hit me up anytime.
At first glance, I can already see that the apparent angle to the star, you just left one apparent angle, and you said that the apparent angle to the star is whatever the FE prediction is, and then you added some correction for refraction.
Well, look at the Hefron angle calculation, just a couple lines up. Yeah, there.
Hefron.
Yeah.
Okay.
See, it has
Apparent angle. So you have. Oh, sorry. So hold on. This is not how we do the Hefron angle either, because you said it's the apparent angle, which includes the FE prediction minus terrestrial refraction, minus the astronomical refraction angle. Dude, Michael Hefron does not use refraction at all. How are you going to call this a Hefron angle and you put two different refraction coefficients in there?
because it matches the results of his method when carried out.
Bro.
What?
Well,
This is not his method. This is not his method, bro.
It's but the
Simulate
formula,
it how it's not, and then I can prove it wrong, right?
but the formula matches the results of his method.
Oh my
That's
God.
my
Oh my
only
God.
goal.
I'm not going to sit here on stream and plug in every
God.
value off his spreadsheet. I can tell it's not his method by what I just said.
Well, I
Are you
plugged
being
in
deceptive again, Jesse? Is that what's going on?
No, I personally plugged in a value for Pikes Peak, and let me just read them all off here. Pikes Peak, Blodgett Peak, Cheyenne, Mount Rosa, Blue Mountain, Green Mountain, and Greenhorn Mountain. And every one of them, it correctly matched. So I'm telling you it works. If you find one that doesn't work on it, then we'll look at it. But so far, all the ones I checked worked. I think it worked. Even if...
Well, that's mathematically retarded, though, so.
Hold on a second. Wait. You're saying, let me get this straight. You're saying that by you taking what he did, right, and what he did was literally just use plain trig with refraction turned off. You're saying you took that same data and you plugged it into a formula that uses two different types of refraction and got the same result and it matches both ways.
Do you realize that the red line represents the altitude, the unrefracted altitude angle given by stellarium in the last step of the Hefron method?
This line? No, you just said this 22.2 is the amount of drop over distance on a glob with a 7/6R. You have plugged in the glob into this line.
Okay, scroll up just a little bit. Oh, there it is. See where it says right there? It says X Hefron equals, and then it's like 0.727747. Do you see that?
Yeah.
Okay. Do you recognize that, or are you aware that that is the angle, that the altitude, the star altitude angle, unrefracted, that's given by the Hefron method from stellarium?
So wait, you're saying that this right here this output is in degrees?
That is in degrees, yep. So if you set the observer height and the mountain height and the distance to any of Dr. Hefron's valid data points, which is most of them, then that Hefron angle will be very close to the angle given by stellarium.
I see. Give me 1 second.
Okay.
I have a question. How would a refracted mountain even block a star? So why would we put in like the refraction of the mountain in there?
Good question. Why is refraction in this formula?
Because that's
Twice.
what it took. That's what it took to make it match.
To match a globe.
Well, no, to make it match all of Dr. Hefron's results.
But it wouldn't match. It wouldn't matter anyway, because if the mountain was refracted, then you would not have it block a star.
You shouldn't block the star. That's the reason we turn refraction off. That's the whole point. It
And
doesn't
is
make any
it
sense.
including all variables? That formula?
Well, I mean, I think that there's some assumptions being made here about like curvature, right, Jesse? Aren't we assuming like a globe in this formula?
I'm not assuming anything. I simply used the formula that matches Dr. Hefron's results with using his method.
But you gotta do a bottom up, not a top down, type of thing to like explain it, because you can't just say, oh, this matches it, and that's like, yeah. I mean, because like the mountain, that's the point. It's like the mountain's actually there. So what would happen if you turned off refraction for the mountain? Because that's what he's kind of shown with this, is like the mountain's actually there and it's not being refracted or anything funny. It's like in its like the elevation that it would be predicted to be, without curvature, none of that. And also like the 7/6 hour, I would argue wouldn't even be like valid for, the nighttime based on like, the calculations with the temperature gradients, because we showed that they even out at night either way, but that's another topic. But either way, like a fractal mountain couldn't occlude anything. So I think that we should just turn that part off.
But the globe needs it. You can't do that, Taylor. If they do that, then it's over. So let's keep playing around in make-believe land with two types of refraction on our representation and just say that it works.
Why can't a refracted light wave be obstructed by the mountain? I'm confused.
Well, he's saying the mountain's also refracted.
Yeah.
So something that's
the
refracted.
path of the light, the
There's
overall
nothing
path
there.
of the light is refracted, right? Follows a particular path. If the mountain happens to be in that path, it will be occluded.
So you're saying that this matches his observations, bro? Because right here,
It's feet. You got to do feet.
I'm doing it in feet. This is 2,075 feet and 2,870 feet. Like, what is this?
Okay, hold on. Let me. Which peak is this?
This is Blodgett Peak.
Okay, so the Blodgett Peak observer elevation in feet is 6,808. You got it in meters.
Okay, 1 second. Gotcha.
Okay, so so anything that's refracted cannot block or obstruct other light. Anybody can just look this up. It's very easy to see, because it's like saying like a hologram or something. It's not real. That's just apparent, right? So it's not going to block or obstruct other light.
It's not
coming out.
It's not the refracted mountain that's blocking the light. It's the mountain is blocking the refracted light.
Okay, well, that's the problem. Jesse put refraction for the mountain as well.
That's just the angle that the mountain is at.
No, the mountain's not at a refracted angle because a refracted mountain doesn't block a star. That's the point.
And the
so he added it back in at both points, right? At the star and at the mountain, just like we knew they needed to make it work.
Yeah, but we're not measuring any physical angles here, right? It's just occlusions.
And
Well, it's just a timing interval like GPS and all of astronomy. Yes. Yep.
Should be 94.9
exactly.
or whatever. Okay. There.
Hello.
See? It's right between them, a little bit closer to globe, which is exactly what you get when you do the Hefron method on that data. On that
So
conclusion.
Hefron
I joined the server and I don't.
Now, if you try dragging distance.
Hold on 1 second. If I take his average altitude using, hold on 1 second.
His average altitude was derived from his method, right? So don't get too circular.
Wasn't he trying to disprove flat Earth? So wouldn't the calculations assume flat Earth instead of like globe?
Yeah, you can't use.
Dude, it assumes the actual geometric position of the star too. It's like this whole like moving the star at different locations, adding your adjusted thing that's close to stellarium. Like, is it at where stellarium's at or not? Like, what?
Yeah. So here's the problem. Here's the problem, right? What I can do to check the veracity of this is I can plug in what the height was shown to be through the timing. Now, you could say that's not the actual height of the mountain. That's fine, but it's the occlusion point of the mountain, of the star with the mountain. So what should happen is if I plug in any particular height that uses his timing of the occlusion, this line should always clip the top of this mountain. It's not doing that. And this difference is because of the refraction you put in there.
No,
You're not using his method.
I disagree.
This is not his method, bro.
Well,
you said it matched everything on the sheet, and it doesn't.
Well,
this should be clipping his mountain.
You just you didn't put in in order to get the accurate results, you have to put in accurate data. You put in you put in an elevation for the mountain, which is different than the published elevation. You put in the one that he derived using his method.
But
right?
yes, and that should be.
You can't test his method against his method. Of course, his method matches his method.
I'm not testing his method against his method. I'm testing to see that this star is occluded by this mountain peak with your simulator at his time.
My simulator assumes correct mountain heights put in. So
Okay, either way, I put both in. Neither one of them had this red line clipping this mountain peak.
well, that's because his results didn't. For Blodgett Peak, remember we went over this.
What do you mean they didn't, bro? The star got occluded at a particular time.
Do you remember a few weeks ago when we all went over the math and we all agreed, including you guys, that the Blodgett Peak one was slightly closer to globe? Remember that?
There was a particular star, I think it was like HD 216 718 or something like that.
Right. And by the way, I did all of them and averaged them, and the average is also closer to globe. One is it's 4.77
Average.
arc minutes from globe and 4.92 arc minutes from flat. Yeah, most of those are closer to globe. I think one was closer to flat.
Maybe you can show it getting clipped by putting in his data or whatever, just to clear up Piezo's point. And then I want to get back to the refracted mountain.
Well, Piezo, the big point here is, does the simulator, when given actual mountain heights, accurately match what the Hefron method gives? And the answer is yes. If you were to put the actual mountain height, the published mountain height, in the mountain height field, you would see that it gives the same, or very close to the same angle as using the Hefron method.
At 1 second.
Saying if you add in refraction at both ends, you can make it match the globe every time. That's really impressive.
That's pretty
just
much
like-
all we're
I
getting
don't know
from
how that
this.
would be logical. You can only add in the refraction of the star or something, because
Nope.
you know
You can do it
refraction
both
cannot
ends.
block refract. Yeah, refracted light cannot block other refracted light. That's the issue. Just like if
Now,
you saw it,
9155.
it's not exact, but it's close.
9156. All right, so this shows it clipping at 9156. All right, let me go to the spreadsheet.
Oh, also, try dragging the distance to 16 miles and see what he would have got if he happened to live 16 miles from it.
Why?
Well, because Piezo had said that, expressed some doubt that there was any combination of distance that would have matched globe, and I'm saying that 16 miles in this case will.
but
Actually, bro, it has you. So I just checked it. This point that it clips at, this line clips this mountain at, is 9156, right? 9156 feet. I just converted that to meters, and I got 2,791 meters. The official altitude is 2,870. So that is about 79 meters below the official altitude of the mountain using your formula. This angle to the star this is your spreadsheet. This angle to the star, bam, 9156.
Well, no, you got to go to the center, not at the edge there. Go to the center. Yeah, there you go.
$92.08.
Right, which doesn't match flat or globe. It's equal. It's halfway between, closer to the globe slightly.
2,806 meters.
Remember, my claim is that the Hefron method is not accurate, depending on the circumstance, depending on the distances and the heights.
Well, your method shows the star getting occluded at 2,806 meters, which is still 64 meters below the actual official mountain height.
No, this is not showing star occlusion angle. The red line represents the altitude angle, the unrefracted altitude angle of stellarium when set at the mountain peak at that time.
This is not the unrefracted angle, bro. I just showed you there's refraction in it. Both the apparent angle, which is this is the angle to the star. I just proved it by changing a number and it threw the line off, right?
But
right. So
it still matches the results very closely using the Hefron method. So you tell me why I had to put
dude, none of the numbers, bro. I just plugged this in. Right? I got 9209 ends up being 2,807 meters. Okay, 2,807 meters. If I go to the spreadsheet, you got 2,807. The official is 2,870. Mike's average was 2,829, and the globe was 2,933.
So, does the Hefron angle given by my simulator match the angle that Hefron obtained in real life for this particular?
Does your simulator match the angle Hefron obtained? No, the angle he obtained was at 2,829. That's what I was saying. Was it 28?
Simulator match the angle that Hefron obtained in real life for this particular?
Does your simulator match the angle Hefron obtained? No, the angle he obtained was at 2,829. That's what I was saying. The angle he obtained, if you follow my mouse, right, this is, hold on, 2,829, convert that to, 1 second, to feet, 9281 and a half. So the angle that his predicted was right here. Right here is where this is. See where my mouse is? Right there. That is where his spreadsheet shows that his occlusions happened. So the line that you're tracing is not matching the line of where his occlusions happened.
Okay, do this for me. Let's look at HD 116.718 since that's the one we looked at before. And the red line the Hefron angle should be 1.844444 degrees. So 1.1844. So adjust something to make the Hefron angle equal to 1.184444. Or just set it to, or just go in there, Hefron angle, and just replace the formula with.
Hold on, why are you trying to jump to a different point, bro? Before we go to that, can you explain to me why this right here, 9281, 9281 would be right here, where my mouse is.
I can explain because you don't understand how this is working or what's
No, bro.
going on.
Bro, you just asked me if it matches what he got. And I'm telling you, so what he got, you're saying if this matches what he got, then this line that you painted should be the line that matches what he got, right?
Yeah.
That's what would what else would be a match?
He got 1.1844 degrees. Right? Am I right? What angle did he get for HD 216.718?
HD 216.718.
Yeah, what angle did he get?
1.196. It looks like your formula says 1.168 right here.
Okay, well, for some reason, the 1.196 is not what you and I and everybody got when we all went over it together. But go ahead and put that red line at 1.196. Is it at 1.19? Yeah, okay, there you go.
Yeah. And it shows 9267, and it should be 9281.
So, the angle that he got, which is a little bit inaccurate because that's not what we all came up with when we went over it super careful. But anyway, the point is,
What?
it's still, that is the angle of that line, and it's still not matching the peak of that flat earth mountain. It's significantly below it. And when we all went over it with super careful, we got even a lower number than that. Oh, the mountain elevation that we all used when we all went over it was 94.29, not 90. Whatever you got. I don't know if that's 9.
So maybe I should use a different mountain for this purpose.
What's that?
1 second, Taylor. In the middle of getting to the bottom of something, will take a minute.
No, this is 2870. This is the official mountain height I'm using right here. 2870 meters is 9416 feet. Yeah, but so what I did find just now is that if I plug in the 1.196 that he got on the spreadsheet, at 1.196, he got 2824.9 meters. 2824.9, which is 9268 feet. If I go here, it says 9268 feet. So it looks like this line is crossing 9268 feet correctly.
Yep.
Excuse me.
Yeah, like I said,
At that point,
red line predicts what that angle is going to be that using his method is going to give. And try dragging the distance over to about 16 miles.
Why 16?
Oh, you got the because that's where I think it would match the globe. Because earlier you had said you didn't think there was any combination that would match the globe, and I'm saying 16 would. But you might have to change that fudge factor you put in.
Oh, I was doing that to make it, match. So let me get this straight. What you're telling me, right, is we have here, let's pretend Dr. Mike's method, right? Let's pretend we didn't make any conclusions about the baseline that we're on. We just know that we go out and we measure it, and we take some stars, and we find out what time they disappear. All we know a priori is that stars only get occluded by physical objects, not uplifted mirages of them. And then we take this data and we plot it. You're telling me that in your worldview, we have these very precise coefficients for astronomical refraction, terrestrial refraction. All this stuff is supposed to be a very precise science. I mean, look, dude, we've got to the 5th decimal point paired with second order squared angles. And if we do that, you don't think that it should just match the globe all the time? Because this right here is where the mountain is. How could the star be getting occluded so far above the mountain?
My contention is that the method itself is invalid. I don't posit it as a proof of globe or a proof of flat because I'm showing that it is not consistent. It can give either.
See, I'm pretty sure that when we went through all of these observations, right, the only ones in which there was even like remotely close between the FE and glob numbers was Blodgett Peak, and everything else was like drastically different. And like you're hanging on Blodgett Peak, but we're also calling into contention. Dr. Mike is calling into contention like that might not even be the actual altitude of the mountain. Because if it is the actual altitude of the mountain, how is the star being occluded by a mountain that's below it?
Blodgett Peak and Cheyenne were about equidistant between globe and flat. Rosa was spot on for flat. Blue Mountain was between them, but about 1/3 from flat and 2/3 from globe. And then, of course, a Greenhorn Mountain was 2,000 feet above flat Earth.
I'm looking right now at the list. Blodgett Peak averaged -40 for FE and +60 for glob. That's the closest one you have. Cheyenne's -49 flat and +93 glob, +3 flat and +182 glob for Mount Rosa, -30 flat, +163 glob for Blue Mountain, plus 17 flat, plus 216 glob for Green Mountain. And so I'm just wondering, right? Like, we're way closer with FE on everything except for this one mountain, right? What if it's just that these mountains that are said to be, over 3,000 meters high, what if their actual altitude is just a little bit different than their published altitude? Like, do you think it's crazy to think that the actual mountain could be 17 meters different than what they publish?
Nope.
Because
Probably.
otherwise, how is the globe off by 216 meters when FE's like spot on? Or
Well,
182 meters when FE's spot on?
well, Greenhorn Mountain was 2,000 feet off, and that would be noticed because a lot of small planes would be crashing into it because those pilots are like, okay, there's a mountain ahead, it's a certain height, I'll be 1,000 feet above it. Well, if it's 2,000 feet tall, bang, in they go. So, no.
Yeah, we have to figure out what's going on with Greenhorn Mountain. We already had a conversation about that. I don't think it's off by 2,000 feet. I don't think anyone's arguing that as far as the altitude of the mountain being off by 2,000 feet. But the point being, right, is if it's a glob and your refraction calculations accurately model the glob, then they should accurately model the occlusion timing. Right, because his whole position is a null hypothesis. What are we falsifying here?
Well, that's my question. When we
What?
start going out at the correct distance to get perfect globe matches, then what will we be falsifying?
Shouldn't every distance be a perfect globe match? Because we have refraction accounted for. That's y'all's whole paradigm, is once you account for refraction, everything matches the glob.
Well, no, I mean, let's say,
No?
Here, do this for me. Put in an observer height of 19 feet. Of 19 feet.
What distance you about to make this?
The distance will be 24.74 miles.
Do we have any star occlusion timing data to go with this?
Yes, it's predicted. I haven't gotten out there yet because the weather's been bad and I've been busy with work. But I want to show you what I'm planning to do, and I can give you GPS coordinates and everything. It's all public locations.
Okay.
All right, and observer height. Okay, you got 19 feet for observer height. Okay, oh, you haven't. Okay, there you go. And 2,337 feet for the mountain height. The temperature slider's handy, isn't it?
So you're predicting that you should measure this at this distance. Is that what you're saying?
That's what the simulator predicts using the exact same math that it matches every single other one of Dr. Hefron's valid data points.
Okay. So real quick, if we then just change any variable, why does it not match glob anymore?
Because it's not a valid method for doing either. It can be
No. That's the point here. When you plugged in, see, here's what you did. You derived using a different set of math, right? You didn't use the math he used. You used refraction, which is supposed to correct for optical effects, right? So once you have corrected for optical effects, we should be able to figure out where the occlusion is going to happen. Now, it could make sense, right? It could make sense for the occlusion to happen at a lower point below the mountain peak, because the star could be technically be lifted up if refraction was really like going crazy over here and doing all this stuff. But it would never make sense for the star to be occluded above a mountain peak. And that's
Unless there
the
was
other
cloud.
problem. right? Because
Thank you.
this right here would be saying that, okay, let's say that we do have refraction, right? And that because of refraction, right, the apparent image of the star is getting lifted up, so it's getting occluded a little bit later than the actual mountain peak would show, because it's being lifted. That's plausible. But it would never be plausible to say it's getting occluded by a mountain that's below it. That just doesn't make any sense. This is physically where the mountain is on a globe. This mountain right here cannot occlude this star ever. So what you've done, actually, in my opinion, Jesse, if you've done anything, and once again, it's to be determined, right? This is my first time looking at any of this. But if you've done anything of useful validity here, you've shown how refraction can account for an extra X many seconds added to the occlusion timing because the star is being lifted up higher than its true position, so that it occludes a little bit later compared to the true mountain peak position for a flat Earth. But for a globe Earth, it still should not even be occluded yet, period. So in my opinion, you've actually just done more work to damage your model here. Because how's this mountain that's underneath this light stream occluding the star?
Oh,
It's not.
well,
It's not.
right, and that's my contention, is that the method itself is not consistent with reality.
I think it's that the glob is not consistent with reality there, buddy. You're almost there. You've almost gotten it. You're so close. This we know the star got occluded. These are real world measurements that we have, bro. The star got occluded. It's a fact. But how could it be occluded if this is where the mountain really is? It couldn't be. So the fact that it did get occluded means that this is not where the mountain is. The mountain has to be up here. And the fact that it's got occluded below the mountain peak is because refraction lifted it up and added some extra time to the visible light in the sky.
Well, remember that Hefron angle is not the angle of occlusion, because you move stellarium, forward to the mountain, and that causes the star angle to rise 1 degree per 60 nautical miles, right? Right? We do agree that if you get 60 nautical miles closer to a star, it appears 1 degree higher, right?
Did we just hold on?
Dude.
Did we just come? Go ahead, Alan.
We just came full circle, dog. What the ruck?
Well, it was a question.
Bro,
don't have to answer.
No, bro. What are you talking about? The lad is here on the ground at 0. He calculated 2 different predictions, and as Piezo just pointed out, the timing isn't globular.
Well,
what did you just say, dude? You just said that moving it to where, dog? It was observed not being there from the distance away that it was derived from.
Well,
we talking about?
He keeps equating the red line with the angle of occlusion as seen from the observer, but that's not what it is, and that's not what it's supposed to be. The point is, whether you like the math or not, whether you understand the math or not, so far, this simulator matches every single one of Dr. Hefron's valid data points, and it also lets us see where we need to go to get globe results. And so my question is, if I go, like I said, 24 miles from this mountain and get a star occlusion timing and it matches the globe, have I invalidated anything, or have I just brought refraction into the equation? Refraction that just happens to make it match a globe.
It's impossible though. Like, so
let
if
me
you
ask
turn
you a
off
question, Jesse. If you're using a wrench on a bolt that's too small to grip because it's like a big wrench, right? Do you conclude that the wrench is not a valid tool?
Well, no, but I think we agreed that 24 miles and 10 arc minutes was not too small to tell the difference between them, right?
Mm-hmm.
Okay.
Let me ask a question. Is the 4/3R, is that
Jesse,
required to get your timings? Do you have to add mountain refraction to get your timings to match?
Yes.
I just use the Hefron method as published.
Then
This
turn off the
isn't.
mountain
This is not the
refraction
published
instead.
Hefron method, by the way. Like, I need you to.
Yeah.
Okay, I just need you to
Yeah.
acknowledge that first of all. Like, whatever you think you're doing,
Oh no,
whether
no,
it's valid or not, this
Hefron
is
had
not the Hefron method.
Hefron had nothing to do with the creation of the simulator. But
Okay, so you said that
used
this was the Hefron
simulator.
method.
I used
Yeah,
the
you
simulator.
repeated. Hold on a second, Jesse. You repeatedly call that the Hefron method, the Hefron angle, right? So like,
But it's not.
It's not though.
But it
So
matches.
no, it's not.
But it matches the angle that he got on all of his valid data
Bro,
points.
it's not, dude. You haven't.
It's
You have
dude,
refraction
we
incorporated. That's not the method.
We literally
Well-
just went through it, and it doesn't show that at all, man.
Well,
Yo, I'm gonna go ahead and wrap up for the night while we're all
Yeah.
still cordial.
Thank you, Alan. I do
yeah.
appreciate the effort.
Yeah, no worries, man. And again, apologize for being so just abruptly rude on last Tuesday. It was uncalled for. But yeah, I think today we've reached our maximum ability to conclude and communicate effectively here. So why don't we call it a wrap here and reconvene next week?
Can I just real quick, Alan? How you doing? And I really appreciate the disclosure you just made. I think it's really big of you to admit that publicly. So big up on you for doing that. And I hope the lads are doing well. I see you. All the lads are here. I'm just curious if you guys would be up for formally doing more measurements of this type, and then from what we find, creating an actual p-value. Because I like, I gotta say, I like that you're looking into the null and alternative hypothesis. It's a good start. I'm just curious if there's been, because on the basis of a single measurement, as scientists and statisticians, we generally don't conclude against it, or we don't generally make a conclusion one way or another as to reject the null. So
yeah. So we have 37 measurements from different distances, or you that incorporate 7 different distances. And we also have 2 locations that people have done their own, and those distances and stuff are not published.
You're probably gonna get a
It's at
good
their house
p-value.
as well. But yeah, I
Yeah, you
agree.
think so?
P-values are tight and stuff. We should definitely p-value it up for sure.
So do you think it would be appropriate of me, if that happens, to say that it's not a real p-value? Just asking. Would you be angry if I said that to you? Would you be angry about that?
More one, I don't think I could ever be angry at you.
Well,
I think it would be around like
it's just that Piezo is here, and
0.8 turns, maybe.
Piezo slandered me. Piezo slandered me personally and professionally.
Morty, this isn't.
No, I'm just curious
to hash out that. Keep it to.
Well, no, it is. It's a public forum, and I was slandered publicly. I'd like Piezo to respond to that and see if he wants to back up his public and professional slander of me as a person. Go ahead, Piezo. Because I'm not gonna tolerate that.
Yeah. Alan's running the outro. I guess.
So
you
just
could if you
on
want.
record, that's very non-Christian behavior. So that's all. And no disrespect to you, Alan. Not trying to just derail your presentation, but
That's
I've
derailing the
confronted Piezo about this
presentation.
privately
That's
several
why.
times, and he has never made an apology to me, and I think that's incorrect.
That sounds like something you and Piezo should work out.
But he won't. Just like he won't do it now. So just pointing that out. Have a good night, guys.
Just so.
Oh, he left.
Okay.
Why did he leave? Weren't you
I
about
don't
to
know. I was
respond?
starting to talk.
He just tried to hijack the whole presentation for his own purposes.
I don't know.
You guys please do something with this measuring of the speed of light, and we can get somewhere in that. I don't know what you guys do, but do it up.
What did you
Well,
say?
I think we learned some really good information here today. I personally didn't know that for the Hefron method you had to refract the mountain. I think we'll have to work that out in the future, see what's going to happen from that. But
I'm gonna be honest, Beast. What exactly did I say? It was too long ago to remember. I just know it was last year, and it was back when we were talking about Aries and all that different stuff. And there was something that came out about p-values. And apparently I accused him of something that was slander. But like I said,
well,
I don't remember because it's been forever, and I don't save stuff like that in my brain.
I mean, so what now? We do Jesse goes and gets a measurement. We go get 30 more. Is this all about just who gets more measurements at this point, or?
Well, it sounds like they don't have any right now, so
that's really the key.
It's just a goose egg on the globe side. Sounds like at the moment. without having to do like a calculation afterwards.
Hopefully you get a clear night, Jesse.
Yeah, I'm hoping too.
I mean, the thing is, let's say that both, like, if there were 37 on each, then the next question would be to replicate them. So, to be able to replicate, like, you know, and then that would give you even more validation on both sides. For example, if two people claim they're getting a different result, and then if they swapped positions, basically, I know that would take the travel and all of that as well, but to be able to then, you know, do it independently to validate it, because if one person has something going on that's faulty, then obviously that would have to be checked and verified to make sure that, you know, that it's not just something that was going on in what they were, the way that they were doing it.
So I did find on Google Earth a public park that was 16 miles from Blodgett Peak, and I did send that information to Dr. Hefron, because I think if he were to go to that location and do his method, he himself would get a globe result, but he was uninterested at the time.
Well, that's what I'm saying. You go to this one spot. Now we have 36 that agree with us, and you got one that agrees with you. So
Well, you
where do you
started
go from there?
first.
Yo,
Yeah.
lads, I'm gonna head off for the evening. You guys have a good night. We will resume the Celestial Theody on Monday.
Good night, Alan. Thank you so much.
Peace.
All right,
Yeah.
Alan.
Cheers, Alan.
And now I'm wildly confused because this Dr. Mike guy said he falsified your thing. Your whole globe's falsified. And now you're gonna
Yeah, so
unfalsify his falsification though? Like, how's that? I thought you could falsify things, and that was a
well,
rat.
yeah. Well, the thing is those most of those measurements, Jesse was like giving a theoretical thing where he could make it line up or whatever, but none of those measurements, not most, none of them lined up with that, like at or below that Green Mountain Peak. All of them lined up at or below the purple one, which is the FE peak, but not the green one.
Well,
And
they lined
you
up
couldn't.
above and below.
There were some below.
The flat Earth peak, above and below.
That's
the
what I
flat Earth
said.
peak.
The
Yeah.
purple one, there were some. Okay, above and below both of them.
Right. No, above and below the.
Are you
the flat
talking
Earth.
about Pikes Peak?
Pikes Peak was above, and Greenhorn Mountain was way above. And if you want, we can go over the math on Greenhorn Mountain. I did it very carefully, but maybe I made a mistake. But I did 6 of them, 6 occlusions, and they were all around plus 2,000 feet, give or take a little bit. But I don't mind if you check my work. I'll send you my spreadsheet here. It's on lines 33 through 38. Oh, and I found that the source for the refraction angle thing, it was from a book titled something about celestial refraction. I gave you a link. Or about celestial navigation. A short guide to celestial navigation.
Ooh.
So Jesse, just the raw observation, the raw timing, without any other, any other calculations afterwards. Do you think you can actually get those that actually show the globe, or no?
Yes.
You say you can. Okay. So if they have 37, you think you can get 37, or not only you, but others that are purporting that this would fit a globe?
Yeah. Yeah. No, it's just it's a matter of being in the right place.
And then if you replicated the ones that they did, then and if they're planar, then how do those fit a globe? How would those ever, if you replicate them?
The way I see it, if a method can show Earth to be a globe flat or concave, depending on where you happen to be, then the method is invalid. It's like having a ruler that randomly changes size plus or minus 50% all the time.
Yeah, exactly. I'm just kind of extrapolating out. Well, I mean, I hear you. Yeah, I don't think anyone's suggesting that the Earth changes shape as you move location. Or I mean, there's elevation changes, but I don't think anyone's saying it's planar over here and globular over there. Although there may be some, maybe like simulation theories or something, or somebody might have thought of that. But yeah, we're not. I don't think anyone's saying that. But yeah, that's just why I'm extrapolating out what if you're claiming that you will be able to get these results, then it's just the extrapolation of how that plays into. But I guess you would have to get them first, and then, or get the first one at least, and then that can be looked at. But it's just the extrapolation of because if the Earth was a globe, that's what I was saying. Like, do you think it can be done with the raw observation, or does it always have to be calculated for? Because if you're saying it always has to be calculated for, then that's a whole different discussion. But if you're saying you can get the ones raw, then it's just a matter of actually getting them, for you to purport that that's what the actual tilting away of the mountain essentially is actually there, rather than just it all being coplanar.
Yep, I am definitely working towards getting my own occlusion timing video, and I've got 2 spots picked out, one which would give a tiny globe Earth, smaller than the globe Earth using the Hefron method, and one that would match globe.
You know of anyone else that's even trying it for the to get an actual timing that would match a globe? Is anyone else even trying it that you know of?
Not that I know of, not the timing that would specifically match a globe. I know John was talking about getting one that would give tiny Earth, a tiny globe, smaller than globe, but since I hadn't released, or since I didn't since we didn't come up with this simulator until last night or so, or was it the night before, it hasn't been easy for anyone to find out what distances it takes to get a globe result. But now it's super easy to find out what distance you need to be to get a globe result. So hopefully we'll get some participants.
Couldn't figure out how to cherry pick the data until you incorporated refraction into the Hefron method. Congrats. Couldn't figure out how to cherry pick the data until you incorporated refraction into the Hefron method. Congrats.
Well, remember that the simulator, I'm not using the simulator as evidence. I'm simply using the simulator to help me to know where to go to get globe results. From then
to get a
on,
result that you're looking for, rather than being, objectionable and just taking in the data as is.
Yeah, but the point is, if I can demonstrate that that works, that the distance affects it that way to match flat or globe, then I've demonstrated that the method is invalid because it gives contradictory results, even though it's being followed to the T, to the letter, right?
That's what you're going for? You're not trying to get data that actually shows a globe. You're more trying to do what you just said there, trying to poke holes at the method and hope that that's compelling.
Yes, I'm trying to demonstrate that the method itself is invalid, which would then invalidate the meaningfulness of all the measurements that were based on that method, right?
Okay, so if that's the case, then what part of his method do you find invalid? What's wrong with it?
The fact that it can give flat globe or concave or tiny Earth, just depending on natural variables that are not controlled for in any way by the method when followed to the T. Don't you agree that if a guy that just happens to, his house is 16 miles from Blodgett Peak, and if he measures and gets globe results, and then a guy that's 42 miles from Blodgett Peak. He measures and he gets a flat Earth. They're both following the exact same method to the T, but one gets flat and one gets globe. Don't you agree that the method is invalid if it gives two contradictory results?
No, because what you're doing is you're trying to find a distance to where it's negligible, therefore invalidating the method. But when you go to the extreme distances where you can actually tell the difference between flat and globe, and then you see that it actually measures more towards the flat side, you go, oh no, it must be the method that's wrong.
No, it's not. It's not the negligible thing. In my example of 24 miles, 24.74 miles, we all agreed that 24.74 miles was significant enough, and that the expected
So
11
not
arc,
16 miles.
and that the expected 11 arc minutes would be non-negligible, right?
24 miles, correct, not 16.
Well, I switched to my mountain that I was talking about because you think 16 is too close for some reason. Although that's still, even 16
So you
miles,
brought
that's
up something that we agreed upon, 24 miles, and that it would be a 10 arc minute difference, which would be enough time to differentiate between the flat and the globe. Now you're moving it closer to 16, which we didn't agree upon. That would be a difference that would be easily seen. What
well,
would be the difference at 16 miles?
well, let's see what it would be.
Yeah, let's see.
I mean, Blodgett Peak was only 22 miles. 16 isn't that much closer.
Not answering the question still.
Let me see how I would calculate that.
Still waiting.
Yeah, well, give me a little bit here. I'm gonna get those numbers for you. And anyone else that thinks they're quicker at math than me can do it too. It's a simple trick.
Would it be would it be possible to do this like in two directions, where you could be in one location and you could be seeing a star rise and a star set at the same time to two mountain peaks, like one like 180 degrees from each other?
It's possible. It'd be hard as shit. Because you'd have to be able to see two mountain peaks in your vicinity unobstructed, and then also have two stars that have the same zenith occlusion. Like they would be occluded at the exact same time.
Yeah, I guess it would have to be like the moment that a star is setting, and then the moment and then the moment that one is rising 180 degrees on the other side of the celestial
Why?
sphere. Essentially. Well, I was just wondering if it would help being in the center, just that you would be able to get like double the distance, and then
I
if
kind
it
of see
were
what you're saying, but that
if it were globe, it should be on both sides happening. Whereas if it's all coplanar, then you would get all coplanar. It would like double the distance potentially. Or not really double the distance, but you put yourself in the middle, and then if you do two of them, kind of like a cross site. I was just it just came to my head, and I was wondering if that would if doing that would assist in because the shape difference would be even more relevant or even more present if you were to have two of them that should both fit essentially like the way the mountain would be tilting way, and then the timing that would be different if it was on a globe.
right. Jesse, you come up with the difference yet?
I'm working on it.
All right.
It's looking like half a degree, but Google recently updated their math engine in their search calculator, and it's doesn't always parse units correctly. So I need to check this by hand on my calculator.
Oh, I was glad Dr. Mike was able to stop by.
I wish I had gotten the answer to that was just one last question. If Alan had let that guy go on 10 seconds longer, I would have got the answer. It was slightly off topic, though. A little bit off track.
Just a little bit.
What's up, though? What's new, guys?
Nothing. Enjoying my days
I was
off.
thinking about light earlier, right? Like, you know how you jump in the car and it's like 0 to 60 in like 2 point whatever seconds. You know what I'm saying? Light's just instant, right? There's no like 0 to whatever. It's just like bam, instant light speed. Faster than the speed of light speed. You know what I'm talking about?
I don't know what you're talking about, Jeremy.
Bro, you get in your car, you go 0 to 60 in like 7 seconds. You probably got like a 7-second car or something, right? There's that. So the light, like boom, like you start the light and it's like it don't go 0 to light speed in however much time. It's like instant, right? It have to be.
I think the term is rate of induction.
Yeah, it does traverse through the environment. You're saying it doesn't do that? If you turn a light bulb on, it has to go from the bulb outwards through the ether.
Yeah, but I'm saying it has to be instant. And at least in like the global paradigm, like they don't have no like light speed takes a second to like get going like your car. You know what I'm saying? It takes you to like a couple seconds to go 0 to 60. They must have to say like it's instant, right?
Oh,
Like
you
it's
mean
instantly going like.
Oh, I see what you mean. It doesn't have to ramp up to that. It just instantly starts at that. That's what you're saying?
Yeah, there is no 0 to 60 time. It's just you're instantly going 60.
Right.
Like
Right.
in 0 seconds, I'm going 60.
Got it, Beasticles.
Yeah, no, I see what you're saying. I've likened it to like spinning a crankshaft. Like if you grab a crankshaft at one end, if you spin it, how long does it take for the other end to spin? Same thing inside the field.
Yeah, it looks like about 7 arc minutes of difference between flat and globe at 16 miles. Or arc minutes, I'm sorry. Did I say arc seconds? Arc minutes. 7 arc minutes.
That would correspond to 28 seconds. That should be enough time.
Yeah.
Okay. We'll see,
You gonna
Jesse.
turn the mountain refraction off?
So anyway, it would be.
Are you using astronomical refraction?
It's terrestrial.
Well, if Dr. Mike were to go to that park I sent them the address to, that public park, and do it from 16 miles, then he would use his method however he does it. I wouldn't even be involved in the math. I mean, I would double check it, but you could trust him. You wouldn't have to rely on me to do his math for him.
Do you think with his method without refraction, he would get globe?
Well, he only has one method so far, and that method, I do believe, would give him globe if he went to that park 16 miles away.
With no, yeah, okay, so with no refraction.
Well, he tells you that it has no refraction. The way I understand it, that I went over in my other presentation, that is part of how he arrives at his conclusion. But that's none of my business. The point is, he has a method. It gives an angle, and the simulator, which matches all of his other valid data points, says that if he goes to that park 16 miles from Blodgett Peak, he will get the globe results using his same method.
Without applying any refraction, you think he'll get globe?
Yep.
So then, what do you think would happen at that case? Like, what would your model with refraction give you that wouldn't give you globe?
I'm not sure what the question is.
So if he gets globe with no refraction, then you obviously would not get globe with refraction. You'd get something else.
Refraction's really not part of the Hefron method in the way he describes it. He describes it basically, you record the time that a star sets or occludes behind a mountain. Then you take the coordinates of the mountain peak that occluded the star, and you put that into stellarium. You turn off refraction. You read the altitude angle for the star at that moment in time given by stellarium, and that is taken to be your true elevation angle to that mountain. That's his procedure. And I'm saying, using his exact procedure at 16 miles to Blodgett Peak from that park would match the globe very closely.
All right.
Well,
we'll
that's a
see.
prediction.
That is my prediction. And I did suggest that to him and a month or two ago, and he was not interested, which is, it's his prerogative.
I wonder if there's any of the data you can reconcile without using the 7/6R terrestrial refraction.
Well, we can always throw out 7/6R and just do trig and measure, and at least we can agree that Earth is a ball, but it'll just have to be a little bit bigger. That's all. But it still won't be flat.
Well, we'd have to go do his measurements. I mean, it's hypothetical.
I've done a lot myself.
Oh, you've done a lot of celestial theodolite stuff?
No, a lot of plain trig measurements. I still need to do my first celestial theodolite measurement, but I've got 2 spots picked out, and I've made a little mount to put a GoPro on my night vision scope, which will help me see dimmer stars better, hopefully. And I've figured out that my GoPro keeps the best time. The Handycam doesn't run at a constant rate, but the GoPro runs at a pretty constant rate, so my timestamp should be very accurate. And I've got a portable battery operated ham radio rigged up so I can get the exact atomic time from Boulder, Colorado via the shortwave radio, and that'll go into the soundtrack, so we'll have that to confirm the time.
Very nice, very nice.
You should live stream it when you do it.
Oh, I wonder. I will 100% see if I have enough cell signal out there. I live in an area where cell signal is kind of an afterthought. It's good in some spots, but bad in a lot of spots. But I'll see. If I can, I definitely would try. In fact, I've been thinking I would really like to get a Starlink Mini that I could take with me when I go on my experiments, and then I could definitely live stream from that. But they're expensive, so I haven't done it yet.
They're like 300 something.
That's not the mini, I don't think. Is it? Let me look.
Or 400.
Yeah, almost 500.
At Best Buy.
Oh, there's an Amazon seller for 370. Home Depot 500, Walmart 400, Best Buy 499.99.
Oh, they got the highest.
But anyway, yeah, I definitely have thought about getting one of those. I still may, but it'd be real nice to go up on a mountain peak and then live stream a simultaneous reciprocal zenith measurement or something.
Are you ever gonna do that one with the force the line thing with the buoy?
Oh, I sure hope to. I definitely hope to do that this summer. Enough of the things to be done are done that I should be able to get the rest done and do it this summer. I'm gonna try. I got way too much money and way too much time invested in that to not do it.
Do you know what Mord one was talking about with Piezo? Because he said he forgot, but I was
No,
gonna
I
go
don't
like remind him or whatever.
know.
Magnetic. If you other
Yeah, so you can spin the copper and it'll create a charge. And you can spin the copper and the magnet and it will create a charge. But if you spin just the magnet, it will not create a charge. And it shows you that it's not the position of the magnet, it's the position of the magnet within 3D space. Yeah. It's a thing.
You lost me.
So if you spin the copper against the magnet, it works. If you spin the copper and the magnet, it also works. But if you spin just the magnet, it doesn't create a charge. It won't work.
You sure
I mean,
about
this Faraday, yeah, it's a paradox. This Faraday guy must have been something, dude. He got a paradox. He got a cage named after him. What else has he got?
He has an effect, the Faraday effect.
Come on. What else?
Fuck, this guy should be on a coin or something. Jeez.
I don't know. He's kind of the one who came up with magnetic force lines.